Welcome everyone to the internship project presentation on the completion of our Emertxe Online Embedded System internship. My name is Bigit. I am currently pursuing my MTech in CSE from NIT Nagaland. I am joined by my friend Ritisha Nayak from Kalinga University. Emertxe is renowned for providing top-notch training in embedded system and IoT, making it a prime choice for enthusiasts like me. This internship has been a valuable opportunity for me to deepen my understanding of IoT. Throughout this internship, I have had the chance to not only brush up my skills but also delve into vital components of embedded system and IoT. Today, through our project's explanation, Ritisha and I aim to share our learning and experience with all of you. Thank you for joining us on this journey. Our contents consist of introduction to the internship project on embedded system, overview of embedded systems and their significance in modern technology, brief overview of the C programming language and its relevance to embedded system development, explanation of microcontrollers and their role in embedded systems, overview of the software tools used in the project, description of the peripherals involved in the project, and lastly, demonstration of the project in action showcasing its functionalities and features. Moving on, let's move on to the introduction slide. Washing machines are household appliances designed to efficiently clean clothes and other fabric items through various washing cycles. They offer a convenient solution to laundry chores, allowing users to automate the process of washing clothes, saving lots of time and efforts. In many households, the washing machine is considered an essential appliance, streamlining the laundry process and improving overall cleanliness and hygiene. Modern washing machines are equipped with advanced features like programmable wash cycles, temperature settings, and load sensing technology for optimal cleaning performance. In this project, we have built a simple washing machine prototype using PIC 16F877A microcontroller. Since we would be talking about embedded systems more throughout this presentation, it is better if we familiarize ourselves more with what embedded systems are. So, embedded systems are specialized computing systems designed to perform specific tasks with a larger system, often with real-time constraints and limited resources. It is combination of both hardware and software electronic gadgets to do a specific task. These systems typically consist of a microcontroller or a microprocessor as the core processing unit, along with supporting hardware components such as sensors, actuators, memory, and communication interface. They also run specialized softwares tailored to the specific application requirements. Examples of embedded systems include microcontrollers in household applications like washing machines, industrial control systems in manufacturing plants, navigation systems in automobiles, and medical devices like pacemakers and insulin pumps. Now let's see what are the types of embedded systems. These can be categorized into two ways. Based on performance and functional requirements, there are four types: real-time embedded system, networked embedded system, mobile, and standalone. And on the other hand, based on the performance of the microcontroller, we have low performance, medium performance, high performance, and ultra high performance. Now let's describe the embedded system based on the performance and functional requirements. Firstly comes real-time. Embedded systems designed to respond to inputs and produce outputs within specific time constraints. These systems are critical for applications where timing accuracy is essential. Some examples of real-time embedded systems are automotive control systems and medical devices. Next comes networked embedded systems. Embedded systems connected to a network enabling communication with other devices or systems. These systems facilitate data exchange and remote control functionalities. IoT devices, smart home systems, and industrial IoT are some examples of the networked embedded system. Next, we have the mobile embedded system. Embedded system designed to be portable and run on battery power. These systems are optimized for mobility, enabling usage on the go. Smartphone, tablets, and wearable devices are some examples. At last, standalone embedded system. Embedded systems that operate independently without the need for external connectivity or real-time constraints. These systems perform tasks autonomously without external dependencies. Microwave ovens, washing machines, and thermostats are some examples of standalone embedded systems. Low performance embedded system. Embedded system utilizing low performance microcontrollers with limited processing power and memory. These are often used in simple applications with basic functionalities. Some examples are LED displays, basic sensors, and simple timers. Next comes the medium performance embedded systems. Embedded system employed mid-range microcontrollers with moderate processing power and memory capabilities. These systems can handle more complex tasks and computations. Some examples are home appliances, small consumer electronics. Next comes the high performance embedded systems. Embedded systems utilizing high performance microcontrollers with advanced processing power and memory capacity. These systems can handle demanding computational tasks. Some examples include automotive control unit and medical devices. At last comes ultra high performance embedded systems. Embedded systems leveraging ultra high performance microcontrollers with exceptional processing power and memory capabilities. These are used in critical real-time applications. Some examples include aerospace systems and industrial automation. Most microcontrollers are programmed on certain programming languages. For our purpose, we preferred using the C programming language. So let us walk through together on an overview about the C programming language. C is a highly efficient in terms of both memory usage and execution speed, making it well suited for resource-constrained embedded systems with limited processing power and memory. C allows direct access to memory locations, enabling efficient data manipulation and optimization, crucial for performance-sensitive embedded applications. C provides low-level control over hardware components, enabling direct manipulation of memory addresses and registers, essential for interfacing with peripherals and hardware in embedded systems. C is a widely adopted language in the embedded system industry with a vast ecosystem of tools, libraries, and resources available to support development for a wide range of applications. Now let us look at microcontrollers. A microcontroller is a small integrated circuit containing a processor, core, memory, and various peripherals designed to execute specific tasks within embedded systems. Microcontrollers provide a compact, single-chip solution for controlling hardware components and interfacing with the external world, making them ideal for embedded applications. To build this project, we are using PIC 16F877A microcontroller. Now let us see the specifications of the PIC 16F877A microcontroller. It has 40 pins. It has 5 ports in total, which consist of port A, which has 6 pins, port B, which has 8 pins, port C, which has 8 pins again, port D with 8 pins, and at last port E with 3 pins. It supports serial communication for it has 2 pins TX and RX. It can also support SPI protocol. We have oscillator frequency range from 4 MHz to 40 MHz. Next we see at the softwares used in this project. We have PIC SIMLAB. It is a simulation software for PIC microcontrollers, facilitating virtual testing and debugging of embedded system design. For our project, we will be using PIC Genius, PIC 16F877A microcontroller board. Next we have the MPLAB-X IDE. An IDE is an integrated development environment for PIC microcontrollers, providing tools for writing, compiling, debugging and programming embedded applications. At last we have the XC9 compiler. This compiler for PIC microcontrollers, translating high-level code written in languages like C into machine-readable instructions for the target microcontroller architecture. Next we see at the peripheral devices. Peripheral devices are hardware components connected to a computer or microcontroller, extending its capabilities and functionalities, input, output or communication functions. These consist of LED, tactile switches as digital keypad, CLCD also known as character liquid crystal display, interrupts and timer. Now firstly we look at LED. A light emitting diode or LED is a semiconductor device that emits light when an electric current passes through it. LEDs are commonly used in various applications. LED is an external device connected to microcontroller port. A part is interface between the controller and external peripheral. LEDs are commonly used in various applications including indicator, display, illumination, and as components in electrical systems due to their efficiency. Next we look at tactile switches as digital keypad. In microcontrollers, switches are often used as input to control the operation of the device or to interact with the user. When the button is pressed, the switch turns on, and the button is released, the switch turns off. They are typically connected to specific input pins on the microcontroller, enabling the detection of switch state changes. Moving on, we look at CLCD, which is also known as character liquid crystal displays. Liquid crystal displays or LCD is a flat panel display technology that uses liquid crystal to moderate light and display images or text. LCDs operate by modulating light through liquid crystal controlled by electrical signals. Important pins for interfacing with the LCD include power, which are seen as VDD and VSS, control, which can be seen as RS, RW and E, and data lines, which can be seen as DD to D7, along with the contrast control pin, which is represented as V0, and backlight pins, which are A and K. Now we look at interrupts. Interrupts in microcontroller momentarily pause program execution, triggered by critical event or external stimuli. Internal or external signals prompt the MPU to halt processing, diverting attention to the request. Interrupts are classified as hardware from external sources or software which are internally generated. At last, we look at timers. Timers in microcontrollers are versatile hardware modules used for measuring time intervals, generating precise timing signals, and implementing time-critical operations. They can be configured to operate in various models, including timer counter, pulse width modulation, also known as PWM, and capture or compare modes, catering to a wide range of timing requirements. Timer often feature adjustable prescalers and reload values, allowing for fine-grained control over the timing, resolution, and periods, essential for applications such as motor controllers, communication protocol, and real-time systems.
Hello everyone, myself Ritisha Nayak. I am currently pursuing my BTech in Computer Science and Engineering from Kalinga University, Raipur. I am here to present project demo of embedded system internship provided by Emertxe. Let's begin. The problem statement for the washing machine program is to develop a washing machine interface and simulate it, which displays then allow users to select different types of washing modes on pressing digital keypads and water levels on long press. On start of machine, it should display function running and remaining time, and also it should stop when the lid is opened. Moving towards the working. The working of the washing machine program is as shown in the block diagram. By using the microcontroller PIC 16F877A. First, switches. Input switches provide user control over the washing machine operation. These switches are connected to specific GPI pins of the microcontroller. For power on or start, switch 5 is used. Pause and stop, switch 6 is used for navigation through the menu as long press is done with switch 4. Next, buzzer. Buzzer provides audible feedback to the user events like cycle completion or error conditions. It is connected to a GPIO pin of the microcontroller. LED or CLCD. CLCD displayed information to the user such as current, washing cycle, or error message. It is driven by the microcontroller through the GPIO pins. The motor controls the movement of the washing machine's drum. It's typically driven by motor driver circuits, which in turn is controlled by microcontroller. Microcontroller is the brain of the system. It receives input from the switches, processes the washing program logic, controls the motor and other peripheral accordingly, and sends output to the CLCD and buzzer. Now let's see the working of the project. The project is implemented using the MPLAB-X IDE, where code of the project is compiled. The project is simulated in PIC SIMLAB, where .x file is loaded and run. The project shows display a message in 4x16 CLCD. Scene to press switch 5 to start. The message is displayed till switch 5 is pressed. Once machine starts, it shows a list of different types of clothes that can be washed. We can navigate through these options by long pressing switch 4. Daily, heavy, delicate, whites, stain, wash, eco cotton, woolen, bed sheets, rinse, and dry, dry only, aqua store, auto are the options. After type to be washed is selected, a list of water level options are displayed. Auto, low, medium, high, max are the options. Once we select the water level and add detergent, we can start machine by pressing switch 5 or reset machine by pressing switch 6. Here I choose switch 6 to reset my options. After starting machine, it shows time taken for machine and start washing. When machine runs, the fan also runs. And we can pause machine by pressing switch 6. The machine washes clothes in 3 steps, that is wash, rinse and first is wash, then rinse, and spin. And spin. After clothes are washed, the machine prompts a message to remove clothes and buzzer buzzes. The machine is redirected to the clothes options page. Conclusion. The washing machine simulation using PIC SIMLAB serves as an effective tool for learning and applying concepts in embedded systems. It offered a hands-on experience that complemented theoretical knowledge and provided a foundation for further exploration in the field of automation. Thank you.